Hello, this video will be about circular motion, and in this case, we will be examining when an object moves in a circular path at a constant speed. Now, the object doesn't move at a constant velocity because the direction of its movement is constantly changing as it's moving in a circle, which means it's accelerating. But even though it's accelerating, its speed isn't changing, which then also means that its kinetic energy isn't changing, and we'll see why in a bit later. So if we draw out this path, the path of an object, it's going to be moving in a circle at a constant speed. And let's just say this circle has this radius r, and the object is moving with speed v. Okay, so since we know the object is accelerating, there must be a force that is exerted on the object. And so we want to find the magnitude of this force. So the direction of this force has to be perpendicular to its velocity, instantaneous velocity, because the speed, as we said before, was constant, which means that the force must be perpendicular, because if there was a component of force parallel, then that would mean that the force is doing work on the object, which then changes its kinetic energy, which then would mean speed is changing, which we know is not true. So that means that the force has to be either perpendicular to its velocity or zero. And since it's accelerating, it can't be zero. So we know it's perpendicular. Another way to gain intuition into why the force is perpendicular, and it's directed inwards towards the center of the circle, is because, I'll just draw it here. Like, say you have a mass attached to a string and you swing it in a circle. When you're swinging it, you can feel the string have tension in it, and that tension is what provides the force that keeps the object traveling in a circular path. And that tension is always directed towards the center of where you're swinging, which is the origin or the center of the circle. So that's another way you can gain an intuition as to why the force is directed inward and perpendicular to the object's instantaneous velocity. Now, the instantaneous velocity will always be tangential to the circle because it is tangential to the path that the object follows. And we'll call this force the centripetal force because it is directed towards the center of the circular path. Now, if we want to calculate the magnitude of the centripetal force, we can do this by using a clever way of comparing similar triangles. So let's just say that this object here travels a little bit, so it travels an angle here, an angle theta, or I should really say an angle change in theta, in a certain period of time. And so this is its initial velocity, and then this will be its velocity after that certain period of time. Okay, and then the distance it travels here is going to be this arc length. So this here is going to be change in x. Okay, so now if we draw these two velocities next to each other, we have v2, and this is v1 right here. And then the angle between them will be theta, because as you can see here, this velocity rotates by angle theta. Now the difference between these velocities is going to be v2 minus v1. And so the change in velocity is going to be this vector right here by vector addition. So this is the change in velocity. Now we know here that each of these, so this is, so if we look at this wedge of the circle here, we know that each of the side lengths of these wedge is r, because that's the radius of the circle. So if we draw this wedge out here, we have this wedge here, which has side lengths r, and then angle theta, and then this distance here is going to be the displacement, or change in x. Now, as time gets smaller, or as this angle gets smaller, so as this angle approaches 0 or gets really close to 0, so it means it gets really small, we get that this displacement roughly equals an isosceles triangle here. So this displacement, even though it's an arc, as this angle gets smaller, the arc can be treated as a line. And so what that gives us is then two similar triangles. So it gives us two similar triangles here. And then let me label one more thing. So the magnitude of these velocity vectors is going to be v, which is the common speed, the constant speed that the object travels in. So now that we have these similar triangles, we can equate the ratios of their side lengths. So we know that change in v divided by v, which comes from this first triangle right here, is going to be equal to change in x divided by r. So this is the displacement, and then this is the velocity, or so the change in x is going to be displacement, and then change in v is going to be velocity. Now one more thing we'll do is we can divide both sides of this expression by change in time. And so what we get now is that change in velocity divided by change in time times 1 over change in times 1 over velocity, I've just rearranged the terms here, is equal to displacement over change in time times 1 over the radius. Now we know that this term here, change in velocity over change in time, as this change in theta, or the angle, approaches 0, we also have the change in time approaching 0, because it takes less and less time to travel a smaller and smaller angle. So which means that this part of the expression here, change in velocity over change in time, is just going to be acceleration. So what we really have here is acceleration over velocity is equal to this quantity on the right-hand side. Now on the right-hand side, we have displacement over time. And so that's just velocity, or speed in this case, since we're not concerned with direction. And so what we have is acceleration over speed is equal to speed over radius. And if we multiply both sides by velocity, we get the final expression that acceleration is equal to velocity squared over radius. Okay, so this is our formula for centripetal acceleration. So centripetal acceleration, just like centripetal force, is just acceleration that points towards the center of the circular path that an object is traveling in. Now, we know that force is equal to mass times acceleration. So that gives us that centripetal force is equal to just mass times velocity squared over r. So that's our formula for the magnitude of centripetal force. And then one more thing we can say is that, as you may have learned in something like pre-calculus, we know that the angular velocity of something, so omega, is equal to the rate of angular displacement over time. And so it is equal to the angular displacement over time, or if you know calculus, it is equal to d theta over dt. However, this quantity is also equal to the velocity over the radius. And we can see that because theta here in radians is, so the angle in radians is defined as the side length, which we'll call, or I'll say the change in angle is defined by the change in the side length, or the arc length, divided by r. So if we divide both sides here by t, or a change in time, then we get that this angular velocity is equal to displacement over change in time times 1 over r, which is equal to velocity over radius. Now, knowing this, we can make a substitution here. So we know that velocity squared, or speed squared really we should say, is going to be equal to angular velocity squared times radius squared. So if we substitute that in, we get that centripetal acceleration, which is equal to v squared over r is equal to omega squared times r squared over r. And then one of these r's here cancels. And so we get that centripetal acceleration is also equal to omega squared times r. So the angular velocity times the radius. And then that also gives us that the centripetal force of an object in circular motion is equal to mass times omega squared times the radius that it's traveling in. So this is a way to derive the formula for centripetal acceleration and centripetal force depending on whether you're given the radius and the instantaneous velocity or the speed of the object, or if you're given the radius and the angular velocity of the object. Again, we're dealing with a constant angular velocity or a constant speed in this case. But this formula also applies to instantaneous speed or instantaneous angular velocity. So even if an object is traveling in a circular path but isn't moving at a constant speed, the instantaneous acceleration, centripetal acceleration in this case, is still going to be equal to the instantaneous speed squared divided by r if you're using this formula here, or it's going to be equal to the instantaneous angular velocity times r if you're using this formula here. And so let's see an example of how this is applied. So let's just say you're on an airplane, and you know that when airplanes turn, they bank the wings. So if these are the wings on an airplane and this is a side view, then you know that this airplane, when it's traveling, so let's just say this is the airplane right here. It looks pretty fun. The wings will be tilted relative to the ground, so that's what causes it to travel in a circle. And really you can think of like birds too when they're gliding or anything in the air. And the reason for this, as you can see, is can be calculated using centripetal acceleration and centripetal force. And in fact, we can calculate the exact angle that a plane needs to bank its wings in order to make a turn at a certain radius when it's going at a certain speed. Okay, so if we draw the side profile, or if we draw, let's just say we want this plane to travel in a circular arc here with a radius r. And let's just say its wings here are banked at an angle theta relative to horizontal. So that's the radius. So it's trying to make a turn with a turn radius of r, and its wings are banked at an angle theta relative to horizontal. If we draw a force diagram for this plane here, we'll see that there's going to be the gravitational force Fg equals mg directed downwards, but then the only other force on the plane is going to be lift from the wings, and that's going to be applied perpendicular to the wings. And so this lift here will be equal to, let's just call it F lift. And then this is going to be an angle theta away from vertical, because if the wings are an angle theta off of horizontal, then this lift, which is perpendicular, has to be an angle theta off vertical. And then if we draw the wings here, it'll look something like this. So gravity points straight down, but lift is perpendicular to the wings and upwards. And these are the only two forces acting on the airplane. And let's just say the airplane is traveling at a velocity v here. We want to know what the angle is that the plane has to bank its wings when it's traveling at speed v or instantaneous velocity v in order to make a turn of the radius r. And so we know that the airplane doesn't change elevation on its turn. So that means that the y component of lift, so F lift y is equal to Fg. And what that gives us is that F lift, and then we can see that the y component is going to be cosine theta is equal to mg. Now we also know that the centripetal force, which is going in this direction, so this is the centripetal direction, Fc has to point in towards the left in this case as we're viewing it, can only be supplied by the x component of the lift force. So that means that Fc here, the centripetal force is equal to F lift x, which we can see here is also then given by F lift sine theta. And then if we remember the formula from up here, in this case we're given the velocity or the speed. So we see that the centripetal force is mv squared over r. So we know that this quantity magnitude has to be equal to mv squared over r. And now what we can do is, if we line these up, so we have F lift sine theta is equal to mv squared over r, and we have F lift cosine theta is equal to mg. If we divide this top expression by the bottom expression, we get that. So if we divide these on both sides by each other, we get that. So F lift sine theta divided by F lift cosine theta is equal to mv squared over r divided by mg. And now we see that a few terms cancel here. So we can cancel the force, the lift force. So in this case, we don't even need to find what the lift force is to calculate the angle. And then we can also cancel mass here. And what that leaves us is tan theta is equal to v squared over gr. So this gives an expression relating the angle that the plane has to bank its wings in order to make a turn of a certain radius at a certain speed. And so if you want to get the expression for the angle directly, it's just theta is equal to arctan of v squared over gr. So that is one way that you can apply the formula for centripetal force in order to find a quantity like this. Okay, let's look at another scenario. So let's just say that you have a circular pendulum. So what that means is you have something like, you know how a normal pendulum would be like a mass attached to the end of a string here, and then it would swing back and forth. Well, a circular pendulum is when, instead of swinging back and forth, you have a mass that's attached to a string, but instead it moves in a circle. And so the mass doesn't ever actually change elevation like a normal pendulum would, but it moves in a circle. And then we can find the period of this circular pendulum. So if I redraw this a bit better, let's just say that we're looking at this circular pendulum and it's at one end of the circle currently. We know that, let's label a few of these parts. So let's just say this string here has length L, and the circle it travels in has radius r, and the distance from the center of the circle to the top where the string is attached, we'll call this distance h. Okay, and then we'll call this angle here theta, which is the angle between the string and this imaginary vertical line connecting the top of the string with the center of the circular path that this circular pendulum is traveling in. And then what we're trying to find is the period of the pendulum t. So t is the amount of time it takes for this pendulum to complete a period or a loop. So how long it takes for this pendulum, the mass on the end of the pendulum, to travel in that full circle. So now, again, if we draw a force diagram here for this mass, we see that for the mass, again, the only forces on it are gravity, which is mg. Let's say the mass is mass m. We'll see that it gets canceled out later, so it doesn't really matter. But let's just say with mass m, the gravitational force is mg, and then the only other force here is the tension force, so on the string. So this is, we'll call that Ft. And then we know that this is going to be at an angle theta off vertical because of, if we draw that line here, we'll see that these are just alternate interior angles. So this has to be angle theta. Now this looks a lot like what we just did above here with the plane. So we can write that since the elevation of the mass isn't changing, we have Ft cosine theta, which is the vertical component, is equal to mg. And then we know that Ft sine theta has to be equal to the centripetal force, because that's the only horizontal component of force, or that's the only horizontal, that's the only horizontal component of force that acts on this pendulum mass, which means it has to provide the centripetal force. And then we know that this is equal to mv squared over r. And now, so what we have here is we can do the same thing where we divide this top or where we divide one of the expressions by the other. So if we divide Ft sine theta by Ft cosine theta, we get that that is equal to mv squared over r divided by mg. And that gives us a similar result above as tan theta is equal to v squared over rg, or gr. Except in this case, we're not trying to find the angle or the velocity. We are trying to find the amount of time it takes to complete a full rotation. And so the amount of time it takes to complete a full rotation is can be given by the velocity, or so the distance it needs to travel to make a full rotation is going to be equal to 2 pi r, and that's just the circumference of the circle. And the amount of time it takes is that distance divided by the speed that it travels at, so v here. So that is the period of the pendulum. And now we know that v here, so v squared is equal to rg tan theta. Tan theta here is going to be equal to the vertical, or it's going to be the opposite side of the triangle divided by the adjacent side of this right triangle. So we know that tan theta is equal to r divided by h. So if we substitute that in, we get that v squared is equal to r squared g divided by h. And so v is equal to r times the square root of g divided by h. And so if we substitute that in for the period, we get that the period t is equal to 2 pi r divided by r times the square root of g divided by h. And then we see that we can cancel the r's, and we get that the period is equal to 2 pi square root of h over g. And so this gives the period of the circular pendulum. Now, if you notice something about this, we see that the period only depends on this gravitational field constant g and h, which is the vertical distance between the top where the pendulum is attached and the bottom of where the circular path that the pendulum travels in. This means that the length of this string that attaches the mass doesn't matter, the actual value of the mass itself doesn't matter, and even this radius that the mass travels in doesn't matter. The only thing that matters for this period is this vertical distance h and gravity, or the gravitational field constant. So what that means is if we have a circular pendulum here that's really long here, or let's just say that it's really close to being vertical, and it's traveling in this small circle here, traveling in this small path, circular path here, but it has height h. It's going to have the same period, so it'll take the same amount of time to complete a rotation as a pendulum where it has the same height h, but it's traveling in a really large circle so even if it's traveling in a much larger circle, as long as this vertical distance is the same, it means that it'll take the same amount of time to complete a rotation for any type of circular pendulum like this. Okay, so that is an interesting result. And then if you look at this formula and you've already learned simple harmonic motion, or have you studied how normal pendulums work, you see that this is remarkably similar to the period of a normal pendulum that swings side to side. Instead, for that, you have the period is equal to 2 pi square root of L over G instead of H over G.